All right, so in this video, we're going to take a closer look at what happens when you have a rational function whose end behavior is linear, meaning like a line, a slanted line, not a horizontal line, but a slanted line. So let's start with an example. Let's find the oblique asymptote for the function, and let's look at the function f of x equals the fraction. On top, we've got x cubed minus 2x squared minus 49x plus 98. And on bottom, we're dividing by x squared minus x minus 12. All right, so this is a rational function, and we've learned a lot about rational functions, but here we're gonna look particularly at the end behavior. So in the past, the end behavior has been dictated by the leading term, and on top the leading term is x cubed. On bottom the leading term is x squared, and when we reduce this fraction we just get x to the first. So normally what we would do is we'd say the ends behave like x to the first, which looks like a straight line growing in the negative direction on the left and the positive direction on the right, and that is perfectly fine. This is for a sketch of a graph, so it's perfectly fine to indicate the end behavior. But sometimes we want our end behavior to be more precise, right? So this is our end behavior of this guy. When your end behavior is a straight line like this, you can find a precise oblique asymptote. And the oblique asymptote is the equation of the slanted line that most closely approximates the end behavior of this rational function. Let me bring up a graphing program and show you exactly what I'm talking about. I've got this function graphed in a graphing program. So this is the graph of the function we were just talking about. You can see it over here on the left side of the screen turned on. And you can see the end behavior does behave like the slanted straight line x, okay? It has that same behavior. But if I were to graph the function f of x equals x or y equals x, let's do it in maybe blue, you'll see, let me zoom out here, that's actually not too bad. But we can get a better approximation. For example, you can kind of see maybe here on the left the blue line and the curve kind of cross, and over here there's a bit of a gap between the curve and the blue line. What ends up happening is actually the oblique asymptote here is the line y equals x minus 1. We're going to solve that in a second, but I want to show you what it looks like. So this red line is what we call the oblique asymptote. It's the line that the curve gets infinitely close to on both ends, and sometimes we want a more precise definition of this end behavior rather than our approximation like y equals x. So we want to find the oblique asymptote. That's an exact approximation. That doesn't make any sense. That is the line that the curve gets infinitely close to on both ends. And we know that this is going to have a linear end behavior because when you divide the leading terms, you get x to the first power. So how do you do it? Well, you do it using long division. So we have to take x cubed minus 2x squared minus 49x plus 98 and actually divide it by x squared minus x minus 12. And I'm going to run through this pretty quickly. I'm assuming you already know how to do long division. We divide the leading term x cubed by x squared, and we get x. Then we take x and multiply it by all three terms of our divisor to get x cubed minus x squared minus 12x. And then we have to subtract all three terms here. So we're going to distribute a negative and change all three signs. The first terms cancel. Then we get negative 1x squared, or just negative x squared, minus 37x plus 98 when we combine our terms. Then we repeat the process. We take negative x squared divided by our leading term x squared, and we get negative 1. Then we multiply negative 1 by all three terms of our divisor, giving us negative x squared plus x plus 12. Now we have to subtract all three terms, so they all change sign. The first terms cancel. Then we get negative 38x plus 86. Now, X squared does not divide into negative 38x plus 86 because this is degree 1 and this is degree 2. So this is our remainder. Okay. Now, what happens is when you divide, and if I were making this video for like a calculus class or something, we would talk about this a little bit more in depth where we have limits to use. But the idea is, as on the ends of your graph, x is getting really big, and when x gets really big, this remainder becomes insignificant. Okay, and I'm going to keep it that simple. The remainder becomes insignificant. So this x minus 1 tells us that the answer we get when we divide, and the remainder basically goes to 0, is that the oblique asymptote, that line that I showed you before, is y equals x minus 1. That's the line that this curve approximates or gets infinitely close to on both ends of the graph. So it's that simple to figure that out. Now, notice it's in the form y equals mx plus b. That's because it's a line. So don't forget, after you get your quotient, you need to say y equals that answer for it to represent a line. Let's try one more. Find the oblique asymptote, and let's look at the function g of x equals the fraction where the numerator is 2x plus 5 times the quantity 3x minus 1, and on bottom we just get 2x minus 3. So in this case, if I want to divide, then I need to distribute the top out to see what I have. So I get 6x squared, then I get minus 2x plus 15x. So that's plus 13x, and then I get minus 5 over 2x minus 3. And we can see, like if we did our end behavior analysis, this function, analyzing the ratio of the leading terms, the end behavior would look a lot like the 3x function. Okay, and that's what we would use to approximate the end behavior. However, when we want the oblique asymptote, we want a more precise approximation of the ends. So we have to divide these using long division. So 6x squared plus 13x minus 5 divided by 2x minus 3. So 6x squared divided by 2x is 3x, like we already knew. 3x times 2x is 6x squared. 3x times negative 3 is negative 9x. Subtract it all. Combine like terms, and we get 22x minus 5. Then we divide 22x by the 2x to get positive 11, and then we distribute our 11 to get 22x minus 33. Subtract it all, changing all the signs. Combine like terms, and we get 28. We can't divide anymore, so that's our remainder. So the quotient is 3x plus 11, so the oblique asymptote is the line y equals 3x plus 11. All right, so that's all there is to oblique asymptotes, just an excellent application of long division. I hope the graph helped you visualize exactly what we're doing here. It's the line that the curve gets infinitely close to on both ends, and it's better than our basic approximation where we divide just the leading terms.